Okay, so let's go over chapter 1. This is an introduction to the course. We'll touch on some of the topics we'll be covering in this course. Okay, so what we're doing in this course is applying concepts of physics to the healthcare industry, to biological systems. Um, Physics answers some of the most basic questions in all of natural science. Okay, so physics sort of is at the foundation of natural sciences. You see it all around us. So, for instance, um, this collective behavior by birds is an energy conservation principle. They do this to conserve energy. You see the bicyclists do this as well. So what's happening here is for a bird to fly from point A to B, you need a certain amount of energy. You'll need a certain amount of energy. So if a single bird flew from here to there, let's say it needs 1,000 joules of energy. Now, if they exhibit this collective behavior, they fly in this formation, each of these birds will spend less energy than that, and that's why they do this. So there's always a good reason behind behavior that you observe in nature. Okay, when they fly in V formation, this bird is working the hardest, and it's easier for all these guys. So the way they do this, and cyclists do this as well, this bird will fly in the front for a little bit and then go to the back, and the next bird will come, and so on. And they share the responsibility, and in effect, everybody saves energy by exhibiting this behavior. Anyway, so physics is all around us, and the color of the sunset, the pitch of one's voice, all have basic explanations in physics. Okay. So we'll learn principles of physics, and applications will be to the health sciences mostly. Okay. And there's a subject called kinesiology. Okay. And the point is the following: we do not have an intuitive feel for how to use our bodies most effectively. Okay. And so kinesiology studies the effective use of that. And so we'll start off by studying motion and examining the relationship between distance, time, and velocity and acceleration. Okay. We'll talk about concepts of force, work, and energy. So understanding these concepts will afford us a deeper understanding of the body, its muscles, and its utilization of energy. Okay. Anyway, so kinesiology is the subject that applies these concepts of motion to our body. Okay. All right. So nutrition and energy. So it turns out that we need energy to do work. Okay. So the point will be to use our energy most efficiently. Okay. We want to get the best bang for the buck. So for instance, here's some efficiencies. You'll see that, so this is the mechanical efficiency of the human body. If you're cycling, your efficiency is 20%. What that means is, for, let's say, 100 joules of energy used from ATP molecules, 20 joules of that turns into motion in the cycle. So efficiency of cycling is 20%. So efficiency is defined as workout divided by output work divided by energy used. Okay, or this is also useful work divided by energy used. You can see that swimming on the surface is less than 2% efficient. Swimming underwater is 4% efficient. So that's why you see when swimmers do jump off the starting board, they try to be underwater as much as possible before they have to come up to the surface. Okay, so shoveling is only 3% efficient. Okay, Anyway, so energy is a central concept in physics, and we'll try and understand that and see how it's important in every situation we consider. Okay. So here's what's happening when we do work. Stored food energy is converted to motion, heat, and other forms of energy. We'll talk about body temperature in chapter 5. You can see that we are a warm-blooded animal, and we try and maintain our core temperature at 37 degrees Celsius. Okay. So when it's cool outside, you don't want to lose too much heat, and so you make a very small portion, just the smallest portion of the core, be at 37 degrees. Okay. So if it were cold and this large portion of a body was at 37 degrees Celsius, you'd lose a lot of heat. Okay. And so you don't want to do that. Okay. So this gives you temperature of various parts of the body. Okay. So this is the situation. This is how your body is when the outside temperature is cold, and this is warm. This is how your body is when your outside temperature is warm. Okay. So warm-blooded animals maintain a constant body temperature. Okay. Now, so all your bodily processes have to go on, but irrespective of what the temperature is outside. So you continue to produce heat as a byproduct of essential processes, even when the surrounding temperature are higher than the body temperature. So what we're saying is, so your body temperature is 37 degrees, and let's say the outside temperature is 40 degrees Celsius. Well, your bodily processes still have to go on. You're producing heat, and now the outside temperature is hotter than the inside temperature. Okay, so the point is, how do you get rid of the heat? Okay, so you will learn in this course. What happens then is, the only way to lose heat then is through perspiration. You sweat, and what you hope is, when your sweat evaporates, for every gram of sweat that evaporates, this evaporating sweat takes away 540 calories of heat per gram. Okay, so when the outside temperature is hotter than your body core temperature, the only way to lose heat is through perspiration and when the sweat evaporates. Okay, so we'll learn all of that in chapter 5. Okay, so this excess heat is, so when the outside temperature is hotter, the excess heat is dissipated by perspiring. So perspiration is the only possible mechanism for dissipating heat when the surrounding temperature are higher than the body temperature. Now here's another problem we face. So normally when you're resting, you're like 100-watt bulb. That is, what that means is you're producing 100 joules of heat per second. And that's what you have to dissipate. So if you don't want the temperature to rise, you're producing 100 joules of heat per second, you have to get rid of 100 joules of heat per second. Now here's a problem that arises. During exercise, much more than normal heat can be generated. So during exercising, when you exercise, you can generate as much as, let's say, 1500 joules of heat per second. Okay, so you're generating 15 times the heat. So your cooling system has to work 15 times harder. Okay, so we'll learn how your body does that. Physical therapy. Okay, so people require physical therapy when they have weakened or damaged muscles. Okay, or suffer from nerve disorders. Okay. Which makes it difficult for them to move their muscles effectively. Okay, so one of the tricks that is used is, now if let's say you're doing physical therapy on land, you might have trouble moving certain muscles or lifting weight, and so if you do physical therapy underwater, you're essentially weightless. Okay, and then you can do stuff that's not possible to do in air during weakened muscles. Okay, so that's one of the tricks employed. So a great deal of physical therapy takes place in water because water helps to support the weight of the person. The buoyant force applied by the water greatly reduces the effective weight of the person. Okay, so making possible to perform exercise that would be impossible out of water. Okay, so we'll study the physics of fluids in chapter 6 or something, and we'll see a lot of applications in biological systems. Okay. So physical therapy can help with all these things: improve mobility, manage pain, recovery from injury, and recovery from surgery. Okay, so we'll discuss the issues involved. So in one of the chapters, we'll study about fluids, and one of the things we'll study is fluid flow. Okay, and to make a fluid flow in a pipe, if you want fluid to flow in this direction, the pressure here has to be greater than that. Okay, so and the flow rate, the amount of fluid flowing depends on the pressure difference, among other things. Okay, it also depends on what kind of fluid is flowing, and it depends on the radius of the pipe. Okay, so for instance, for us, if you're exercising, you want the blood flow to increase. And how do you increase the blood flow? So you can increase the pressure differential. So the pressure differential is P1 minus P2. It turns out you can also increase blood flow by increasing the radius of the blood vessels. And we'll talk about all of that. Okay. Okay, so liquids and gases can be made to move by the application of pressure. Okay. So the heart creates blood pressure differences by exerting force on the blood with a muscular contraction. The flow of blood can be regulated by blood vessels changing diameter. So if you want to increase flow, you increase the radius or the diameter of the pipe, and thereby changing the resistance to flow. So if you increase the radius, you'll learn that the resistance of this pipe decreases, and so the blood flow increases. Yeah. So other examples of body's use of pressure include breathing. So for instance, we will learn, okay, so here are your lungs, okay, essentially alveoli, okay. And what this is saying is, so this is gauge pressure. You'll learn about all of this. Gauge pressure is atmospheric pressure, actual pressure minus atmospheric pressure, okay. So if the pressure is atmospheric pressure, P naught minus P naught will be 0. Gauge pressure will be 0. Okay, so what this diagram is telling you is the pressure inside the lungs is the same as the outside pressure. You know? And we'll learn about all of these. So alveoli are little, you can think of them as little balloons. Okay? And so if you have atmospheric pressure of air inside, this balloon is trying to compress and increase the pressure. Okay, so if the outside pressure is also atmospheric pressure, and the balloon is will squeeze all this air out, and the alveoli will compress. Okay, so how does the body prevent that? What the body does is the pressure here is lower, outside the alveoli is lower. So in the thoracic cavity, you can see that in the thoracic cavity around the lungs, the pressure is lower. That's how the alveoli do not collapse. Okay, and so when you take in a breath, the way we'll learn all of this, the thoracic cavity expands, and the outside pressure drops. Okay, so the pressure is minus 3.44 centimeters of water. The outside pressure drops, and then the alveoli expand and air moves in. And so air moves into the lungs, and then when your diaphragm comes back up, that air is being squeezed. The pressure here is greater than the atmospheric pressure, and then air flows out. All right, well, we'll learn all of that anyway. So there's physics in there's a physics principle involved in everything that happens in nature. Okay, hearing. So here's a pretty awesome instrument that we all possess, and what this does is it converts sound waves into electrical impulses. This instrument only understands electrical impulses. So this device converts a sound wave into electrical impulses. Okay, so, and it does it via in the process, it various parts of the ear amplify the sound. Okay, so the uh, outer ear amplifies it almost 2 times. It's a 10 dB gain, and then the sound waves hit your eardrum, and there are 3 bones that transfer the energy of the vibration of the eardrums to the cochlea, which is where the vibrations get converted to electrical signals, which are sent to the brain. Okay. Now it turns out that this device that we are born with works for frequencies in the range of 20 hertz to 20,000 hertz. Okay. So there are sound waves that are higher frequency, 30,000 hertz and all that kind of stuff. Anything about 20,000 hertz. Anything about 20,000 hertz are called ultrasonic waves. They're called ultrasonic waves. Okay, for instance, so you can produce a sound wave like that, but this instrument can't hear it, but there are other devices that could perceive that sound. Okay. So our perception of sound depends on frequency. Okay. So we'll learn all of that. Okay. So for instance, dog whistles produce high frequency sounds, and so on. So we use ultrasounds, sounds of frequency higher than that, higher than 20,000 hertz in scanners. Okay. All waves reflect. So here's an ultrasound scanner. It's a transducer. What a transducer means is it transmits ultrasound waves, and it can detect them as well. So it's a transmitter and a receiver. And the idea is the following: you send ultrasound waves, and these waves are reflected from boundaries, any boundary. So this wave will be reflected from that boundary, and so on. Okay, and that's so what these measurements are is this is the time delay of the measurement. Okay, so this wave came back after this time, meaning so it covered. So if it came back in 1 second, the object reflecting it is half a second away, because the wave has to go there and then back. Okay, so the object is half a second away, meaning you can calculate the distance. And from the intensity, you can calculate the intensity of reflection. You can calculate the properties of the material. Okay, so from these kinds of graphs, an image can be reconstructed. Okay, so an ultrasonic scanner uses sound waves of frequency higher than what we can hear to create images of images of objects that you can't create using light waves. Okay. They are perfectly safe if you keep the intensity of this beam low enough, the beam low enough, they won't cause any injury. Okay. So you're probing inside the body non-invasively. In one of the chapters, we will talk about electrical safety. It turns out that when patients are undergoing certain medical procedures, they're extremely sensitive to electrical shock. Okay, so while you're fixing the patient with one problem, you don't want to create other problems. So we'll learn about electrical safety. Our nervous system is of course, pretty amazing. You have 90 billion interconnected neurons. Okay, so our nervous system is a complex of biological electrical circuits. Okay, a muscle contraction can be initiated by an electrical impulse. So when your heart beats, it's a series of contractions, synchronized contractions. Okay. So the electrical impulses involved will be studied. So for instance, here's a graph of, this is a electrocardiogram. It gives, and this a graph like this can tell you whether the heart is healthy or is sick. Okay. So if the electrical impulses fire in the right sequence, your heart is beating correctly, and so on. Okay. So we will study graphs like this. Okay, we'll look at graphs like this, and similarly, you can do this kind of. You can do electroencephalograms. You can study the electrical impulses that go on in your brain. So it can be so information can be obtained about brain functions by recording its electrical impulses in the electroencephalogram. All right, so we'll look at all of this stuff. Yeah. Your vision is an important sense that you possess. Okay. So, and when your vision is suboptimal, we'll look at ways to correct them. So, for instance, here's a myopic eye. Okay. Normally, in a normal eye, what you want to do is you want to create an image on the retina. So what this is showing you is a far away object, and its image is created in front of the retina. So this is a myopic eye, meaning this person is nearsighted. And the far point tells you, okay, so this eye, this myopic eye, can only focus up to this point. If an object is here, the image is formed in front of the retina. Okay, so you can't see far off object. And the way to correct this eye is to use a concave lens. Okay, what a concave lens does is if your object is anywhere beyond this point, it forms an image in front of your far point, and then your eye takes over. Anyway, so for a nearsighted person, a myopic eye, a concave lens corrects the vision and forms an image on the retina. This is a farsighted person. Okay, this person, so this is a hypermetropic eye. For this person, the image is formed behind the retina. So this person, what they can see far off objects clearly, but they can't see nearby object. Okay, so for this person, there is the near point of the defective eye, meaning beyond this point they can see. Anything inside of here, they can't focus on the retina. Okay, so a correction for these guys is using a convex lens. Okay, and this lens will form images of all these guys, any object in this range, on the retina. Okay. So the laws of optics is what we need to study to understand all of this, and we'll do that. Okay. We use electromagnetic waves almost everywhere. Electromagnetic waves are waves that can travel through vacuum, that travel at the speed of light, okay, which is 3 times 10 to the 8 meters per second. Okay. And they're called electromagnetic waves because these waves contain both electric and magnetic fields in them. So here's the electric field. The wave is traveling in this direction, and we'll study all of that. So electric fields are denoted by E, and magnetic fields are denoted by B. So this is B. Okay. And we'll see that electric and magnetic fields are perpendicular to each other and perpendicular to the direction of travel. Okay. Anyway, so here are the various kinds of electromagnetic waves: radio waves, microwaves, visible light, ultraviolet light, X-rays, and gamma rays. Sound waves that you studied, ultrasound waves, they're not electromagnetic waves. Okay, sound waves are not electromagnetic waves. So, for instance, and here are these electromagnetic waves, so radio waves, infrared waves, visible light, and you can see that the wavelength, this is the wavelength, and as you go to the right, the wavelength is decreasing. Wavelength is denoted by lambda, and frequency is denoted by f. The speed of light is given by frequency times wavelength. Okay, and as the wavelength decreases, frequency increases. Higher the frequency, higher the energy of the electromagnetic wave. So higher frequency means higher energy. Okay, and light comes in photons. The energy of a photon is the Planck's constant times the frequency. So you can think of light as coming in packets like that. Okay, so these are high energy photons and these are low energy photons. This shows you various things you can use them for. Okay, so X-rays, we use them to make pictures like that. UV light, visible light, our eyes are sensitive to this very narrow band of electromagnetic waves. So our eyes can detect only these electromagnetic waves. Okay. You can of course feel infrared waves. We use microwaves all the time. Okay. So microwaves can be used for deep heating. You can take a big chicken and cook in a microwave, so heat reaches all points. Okay. While ultraviolet waves cannot, so when you go lay in the sun, the ultraviolet waves are absorbed by the skin. They don't penetrate deep. Okay, and they can cause sunburns. Ultraviolet waves can also be used to sterilize objects, even at low intensity. Okay, so we'll study all of that. So spectral analysis. Okay, now here's the thing. Okay, so let me draw the model of an atom. So here's an atom. So this is the nucleus. The nucleus has protons and neutrons. Okay, and it's surrounded by electrons. Okay, so what I'm drawing you is a helium atom. And the helium atom has 2 electrons. Okay, and these are the energy so these are the allowed orbitals. Okay, so when the electron is in a high energy orbital, okay, when the electron comes back to its ground state, it emits a photon. Okay, so let me so here's an excited helium nucleus, and when this electron falls back, it emits a photon. Okay. And the energy of this photon depends on this energy difference. Okay. Energy difference. So every atom and molecule has its unique fingerprints. It has a unique spectra. So again, let's make sure we understand this. Every atom and molecule has a unique spectrum. So from the spectra of the material, you can identify what is emitting it, and that's what spectral analysis is. Okay, so spectral analysis is a useful tool in detection of trace amounts of toxic substances. Okay. So all elements and compounds emit spectra that are uniquely characteristic of the atom or the compound. So it's used extensively in medicine and a host of other disciplines, from chemistry to astronomy. So we'll study that. We all have experienced X-rays, and you can see what X-rays can do. So in the medical field, if you have a broken bone and stuff like that, an X-ray image will will illuminate that for you. Okay. Now we saw that X-rays are high energy photons and they can cause damage. Okay. So, and the more the X-rays shine on you, the more damage they cause. Okay. So, so the use of X-rays, of course, can be hazardous, but okay, we use it when necessary and low enough intensity. So their use is a calculated risk, okay. But that risk is worth taking if you have a broken bone and you need to find out about it and fix it. All right, so in all the concepts we study, all the physical quantities we study, all this, the basic quantities will be length, mass, and time. Okay, and the units, the system we mostly use are SI units, where the length is measured in meters, mass in kilograms, and time in seconds. Okay, and so for instance, things like velocity, energy, and all will be a combination of these guys, so these basic set of units. Okay, so we'll measure entities in the SI system of units. SI is International System International, so that's the in the physical sciences, that's a universally accepted set of units. So meters are units for length, kilogram for mass, and seconds for time. All right, sometimes, so for instance, a meter is a little more than a yard. So this unit of length is quite large. So what you want is, so for instance, if you want to measure the size of a cell, then a meter is not a good unit, but you can derive a unit from the meter, and the derived unit is, let's say, here's a good unit to measure the size of a cell, 1 micrometer. And this micro is a power of 10. All these prefixes are powers of 10. So 1 micrometer is a millionth of a meter. And this is a good unit to measure the size of a cell. And that's what these things are. So the prefixes are, this table gives you the power of 10 the prefixes are equal to. So a millimeter is 10 to the minus 3 meters. A micrometer is 10 to the minus 6 meters. Here is the prefix symbol, okay, or letter. A nanometer is 10 to the minus 9 meter. Is 10 to the minus 9 meter. And this is a good unit to measure the size of an atom, for instance. Okay. All right, so that was a brief introduction to the course. It gives you a flavor. It tells you what we are going to learn in this course, and gives a flavor for the course. Okay.